So, so then the simplex algorithm might not be able to predict this deviation.
Yeah, if coefficient of differential equation change, then attractor shape will be changed. That's why we cannot use this anymore.
So this is what I said earlier. So this is the basic process of the simplex projection algorithm. So we assume that there is an underlying dynamics. We use EVM to construct the delay embedding, and then we use the nearest neighbors for prediction. But we can see here that the effective temperature is not incorporated. So we need this to be explicitly in the equation. So we need dxt to have to be also a function of the temperature. And that is exactly the first assumption to the method here, the MTE-EVM. But the question is, how can we incorporate that temperature? So the assumption 2, which was also stated in the abstract, is that temperature will only affect the rate of the dynamics, but not the form. So, as mentioned earlier, for increasing temperature, we can see that for the low values, the slope is not that steep, so it's slow. But when the temperature increased, the slope here becomes steep, making the rates faster. So this is the assumption. We should note that if the temperature effect is not this and this, here we can see that when temperature increases, suddenly the form or the shape of the abundance changes. We cannot use this method. Okay, so basically this means that temperature will only scale the dynamic rate. In equation form, that means that the equation for the rate of x will be something like this. So we'll just be scaling the function of x, y, and z by a function of temperature. So we are separating these effects. F here represents the effects of all other states, and h of t here is the temperature effect. So we call this temperature separability. So we have to make sure that when we use this, the species actually satisfies this assumption. And we will see later that it might not be applicable to other species. So then here comes the unfamiliar term before. So assumption 3 to this study, to this method is based on MTE. So biological rates will increase with temperature according to this Boltzmann factor, which looks like this. So here, E naught and K are both constants, but T here is the changing temperature in Kelvin. So actually, when we graph this, you will see that if you graph temperature against this Boltzmann factor, it increases as temperature increases. So as you can expect, this is what we will use to scale our dynamics. So yeah, so the goal here is to introduce a metabolic time step such that the metabolic time is faster when temperature is high and slower when temperature is low. So here, we introduce mu here to be equal to the Boltzmann factor. This one satisfies the description of mu that we have set here.
What is a mu? Mu is
We are introducing mu, which we call the metabolic time step, which should satisfy this. So it should be faster.
New variable, so satisfying that equation.
So that if we go back to our equation before for the rate of t, we will be using this value to scale this. And we can see if we multiply h of t here, this will become dx over d mu. Mu is now the metabolic time step. And you can see that the right-hand side will be completely in terms of x, y, and z. So after this rescaling, this is what will happen. So, sorry, this is a wrong notation, so it should be. So after rescaling, we can see that the speed, according to the metabolic time, will be same.
Everyone is okay about this? I think it's super clever. Actually, you learn at undergraduate this time scale thing, right? So basically what they did is what this equation means. When this is a large, mu is also vastly changed. When it's h is low, it's slowly changed. What means t switch to the mu now actually, d mu dt. So when high, here is fast change. Low, here is slowly change. That means fast change means we. Slowly change means we. Shrink. If that happens, then we agree. We believe this theory, right?
So they actually confirmed this using the experimental data. If you remember, this is the graph that I showed earlier, right? So,
Scaling?
yes. So recall that during low temperature, there's slow dynamics. High temperature, the dynamics is fast. So they performed the rescaling into metabolic rate, and you can see that here. Under metabolic time step, the speed is the same for all temperatures.
Wow. They use the exactly same scale. Exponential negative 0.65. That's it. I think activation energy 0.65 and then kappa times measure temperature in Kelvin. So yeah, of course that's not perfectly matched, but yeah, convincing. Yeah, in this room we have two physicists. They will love this. 맞습니까? 심장 뜁니까?
Okay, so basically what the MTE EDM does is just apply EDM to the rescaled system. So recall that we have two equations for the rate of x with respect to the metabolic time step and d mu over dt, the rate of metabolic time with respect to t. So, of course, what you want to know here is the solution for this system, but recall that if we will be dealing with real data, then it is not continuous, so we have to discretize the problem. So basically, if we perform numerical integration here, I didn't write the full form, but we know that if we perform the numerical integration, the xi will just be a function of the previous values of x, y, and z. So after this, we just apply EDM as before. So we can get the lag values of x as before, but this time the time is in metabolic time, which is mu. And the metabolic time can be computed from this equation. So this is just the numerical integration, and then mu I will be of that form. If you expand it to mu 1, 2, 3, you can just get this form. So that for the mu n, it is just the sum of this h times the So this will be the metabolic time steps that you will use for the lag values.
So here we didn't change, just we changed the time step length.
So actually, it's just rescaling
The x-axis, right? Then in the manifold, does it look different? Because I'm confused because to draw the Takens theorem manifold, we need a xt minus tau, x minus 2 tau, right? It should be equal interval. Sampling should be equally done. But how they handle it? They do the interpolation or what?
Oh yeah, so it will not be exactly like equal. So what they did when I checked the code is like if
Between this,
yeah, they approximate it.
so by interpolation.
Yes.
Yeah, so I think point is we have to draw the originally we need xt we need this, right? If we do the equal interval sampling, it's easy. But now, yeah, I know originally we have equal interval data, but now we do the scaling, right? So narrow and then wide. Then, but we need an equal interval data to construct this. So what you mean is we did some interpolation and then we did a equal interval. Okay, I think that's the only thing they can do at this point. Anyway, the point is we only just change the time scale, and then if we apply the EDM again, if we become better, then makes sense, right? Prediction.
Yeah, so we will have same process as before. Right? So, but now this is the lag values of x are in terms of metabolic times. But as Professor said earlier, the time steps are not equal, so they did some interpolation in order to construct this new attractor. So then, actually, we will just do the same thing as simplex algorithm, right? So, for example, this is the current state. We want to predict the next state. What we do is, to predict the next state, find the nearest neighbors again of the current state. These are the blue dots here. And then, again, get the weighted average of the future states of the nearest neighbors. And then, that will be the prediction for the next state. So actually, this is simply the simplex algorithm, but in metabolic time. So they simply rescaled everything and then performed the same process. Then, yeah, that is the process of the MTE-EDM. And then now, the best way to confirm or verify the effectivity of this process is to test it on simulated data. So what they did is they looked at a chaotic system of 3 variables of this form. So function of x, y, and z times the scaling factor h of t. And their first case is that the temperature is linearly increasing through time. So you can see here, as temperature increases, the slope in the abundance graph becomes steeper and steeper. So then, of course, they compared the performance of the benchmark model, which is the simplex algorithm, versus the MTE-EDM. And after evaluating the performance, they tried different embedding dimensions here, and the performance of MTE-EDM is far better than the basic simplex algorithm.
So rather than just assuming rate is linearly proportional to the temperature, I don't know. So the above simplex is we don't consider the temperature dependence.
Yes.
Regular approach.
And then they also tested.
So the embedding is not uniform time, but it's a uniform mu step in that picture.
Actually, I think the notation here is wrong, because it should be like mu minus t 2 times some factor. I think this is confusing. but this should be x of mu minus its minus some lags. I mean, they construct the delay vectors for x in metabolic time.
Yeah.
Which is mu.
Yeah.
It should be mu.
So I mean,
minus delay.
basically we do same sampling time embedding for Takanen zero.
For the simplex
Real
one,
time, real
is the
time.
real time.
Yeah, but in this
In
case,
this case, we use the metabolic time,
Yeah.
the scale.
yeah. So okay, thank you.
And then for the second case, they considered a more realistic graph of the temperature. So they considered a temperature that has seasonality, and they added some noise. So you can see here, if we take a look at the parts where there is low temperature, clearly the slope is it's less steep. So dynamics is slower. And for the higher temperature, the steepness it becomes higher. So we have faster dynamics. They performed the same thing. They compared the result of the simplex algorithm and the MTE EDM. And simplex algorithm slightly improves, but still the MTE EDM has a better performance for different embedding dimensions. So this is the result of the performance on simulated data, but they also, before that, I think one limitation of this paper is that we have the same scaling factor for all species here. So the assumption is that all the interacting species will have the same temperature dependence. So they also tried it on, I think this is 22 different organisms. And here they compared different methods, but we only focus on the MTE, which is the light green, because as you can see from all the comparisons, its improvement relative to the simplex algorithm is much higher compared to the other methods. And actually, when we take a look at these parts, where the improvement over the simplex algorithm is high, if we take a look at the temperature graph, it looks something like this. But if we look at these ones,
Similar performance.
so the temperature is not it's not changing too much.
Really?
So we can expect that if there is more variability in the temperature, then there is higher improvement. But if there is low variability in temperature, there is lower improvement in prediction. So this makes sense because when we rescale into the metabolic time step, since there is not much variation in temperature, then it is more similar to the performance of the simplex algorithm. And actually for these last species, you can see that there is actually almost no improvement over the simplex algorithm. So this is because these three species are not really temperature dependent. So they don't rely on external temperature. So yeah, so that is one thing you have to think about when you apply this method. You have to make sure that the species you're applying this method to is actually temperature dependent. So it has good performance over in simulated data and also in the actual data. So take-home messages. First, the dynamic rate of many species are temperature dependent. And what the MTE EDM does is we scale the calendar time to metabolic time and apply the EDM to the rescaled system. In this way, we can have a better prediction accuracy than the benchmark model, which is the simplex algorithm. So that ends.
Any questions? Yeah, please feel free to. Kevin?
Well, thank you for a nice talk. So one of the most important things in this method is the Boltzmann operator to change mu rate depending on the temperature. But in the discussion of this paper, the author explored the ability to maybe change this Boltzmann operator to another operator. So instead of just predicting the future of a species depending on the weather, the temperature, you can predict the future of a species depending on another parameter.
Actually, they mentioned that briefly in their discussion that this approach can also be applied to other variables. So it is not like constrained to the Boltzmann operator. Like if it's dependent on maybe something else like, I forgot what they mentioned, but you can use something or a scaling factor that is like universally known. And you can expect that the prediction accuracy will also increase over the regular method.
Any other questions? 우민이 녹화인데 조용들어. Any other question?